Hello everyone, this is Shiba, a major of electrical engineering at Wayne State University. My presentation is about a two-layer LSTM deep learning model for epileptic seizure prediction. At first, motivation is obtained. Afterwards, Melbourne dataset or the overview of the proposed model and proposed model will be explained. Then I will talk about the performance evaluation methodology and results performance and analysis. Finally, I will go through the conclusion. Epilepsy is known as a seizure disorder. It is usually diagnosed after a patient has at least 2 seizures that are not caused by some non-medical conditions. Nowadays, more than 65 million people have epilepsy. The patients having generalized tonic-clonic seizures are at the risk of the sudden unexpected death in epilepsy or SUDEP. In general, research focusing on epilepsy can be divided into main categories: research focusing on epilepsy detection and research focusing on epilepsy prediction. For these applications, we can use EEG signals. The EEG signals can monitor the brain activities. In terms of the epilepsy, the EEG signals can be divided in 4 states. The seizure state refers to the time when the seizure occurs. The time exactly before seizure occurrence refers to the predictal state. The time exactly after the seizure occurrence refers to postictal state. And the normal state for the patient refers to interictal state. The goal of epilepsy detection is to detect a seizure. However, the goal of epilepsy prediction is to predict a seizure. In this case, we need to use pre-ictal and interictal samples to train and test our system. There are some solutions to help the patients living with the epilepsy. Here you can see the list of commercial wearable and implantable devices, such as responsive neurostimulation system, EpiHunter, NIL, etc. These devices can be worn by the patients, and some of them are implantable. These devices are able to monitor the brain activity and they can detect a seizure. In this case, the patients don't have enough time to react against the seizure. For this reason, in this research, our goal is to design an efficient and accurate epileptic prediction system. Melbourne dataset consists of long-term intracranial EEG data from 15 patients with refractory or drug-resistant focal epilepsy. In our research, we use a subset of 3 patients with the lowest epilepsy prediction performance from the NeuroVista trial. These data were publicly available in 2016 for the Kaggle competition. Here you can see some details for each patient. And as you can see here, for recording, 16 channels are used and the sampling rate is 400. This data set consists of 2 folders, one folder for train samples and another folder for test samples. In this data set, there is a gap between the train set and test set. This gap may causes the drift data problem. In general, drift data problem refers to the data that there are huge differences between the distribution of test and train samples. Then we need to try to design an efficient system which is able to overcome this issue. Here you can see our proposed model. It consists of several steps. At the first step, the raw data are gathered. Afterwards, a pre-processing step is used to clean the data and do the segmentation. Then we use feature extraction to extract the most important features in time and frequency domains. Then a two-layer LSTM is used to classify the data. For this network, we consider one output, and in this case, for pre-ictal sample, the output is 1, and for inter-ictal sample, the output is 0. Finally, to remove the false predictions, we use post-processing based on a novel method, which is minimum distance. In the following, I will explain more about each step. In the Melbourne dataset, there are some dropout data. As you can see in the features, dropout data refers to the data with very low amplitude. In this case, these data not only don't provide any useful information, but also if we use them during the training, they will confuse our system. For this reason, at first we need to remove them. In the next step, we do the segmentation, and in our work, we consider 30-second segments. In addition, because we want to use LSTM in the classification step, we consider 35 sequential segments. In our work, we consider the system with and without the normalization step. In general, normalization step is used to scale our data into the certain range, which helps to remove the scattering in the data. As you can see here, our goal is to normalize our data into the range between A and B, and xk is the input segment. At first, we find the maximum for the input, the minimum for the input, and based on this formula, we can normalize our data. In the feature extraction, we extract the features in time and frequency domains. In time domain, we extract mean, variance, deviation, skewness, kurtosis, peak-to-peak, number of zero kerosene, energy, and energy distribution. And in the frequency domain, at first we divided the data or segment to 8 frequency bands, and you can see the range of each band here. Afterwards, we extract the power spectral intensity. As you can see here, 8 features are extracted in time domain and 8 features are extracted in the frequency domains. Accordingly, we will have 16 features, and because we use 16 channels, then in total we will have 256 features. In addition, because we have 35 sequential segments, then the input shape for the next step or LSTM will be 35 to 255. In the classification step, we use a two-layer LSTM. At first, we use a standardization layer, and as we can see here, in the LSTM layers, we use 16 memory units, and to avoid the overfitting, we use two dropout layers and with a factor of 0.3 and 0.5, 0.1 for first and second layers respectively, and then we use a dense layer. The last layer is the output, and the output is 1 for pre-ictal sample and is 0 for inter-ictal sample. For training step, we use adaptive moment estimation as an optimizer, and cross entropy loss function is used for cost function. In addition, in our work, Swish is used as an activation function for both layers, and you can find the formulas of Swish in here. As you can see here, we have beta, and in our work, beta is set to 1. In our research, the goal of post-processing step is to assign an output to the 5 sequential outputs from the network. Here you can see we have 5 sequential outputs from the network O1 to O5, and there are the inputs for post-processing step. Based on the method that we use here, we can assign only one output for these 5 outputs here. For this work, we consider 3 methods in the post-processing step. The first one is arithmetic mean. In this case, we calculate the mean for these 5 outputs, and if the mean is more than the threshold, for also threshold is set to 0.5. In this case, the output is 1. It shows that the input is empirical, otherwise it is 0, which shows that the input is interictal. The second method is K of n, and in our research, we consider if 3 or more than 3 outputs are more than the threshold. In this case, the out is 1, otherwise it is 0. The third method is a novel and proposed method based on the highest similarity to pre-ictal and interictal sample. And in the following, I will explain more about this method with one example. Here is an example of 5 sequential outputs from the network, and these outputs are related to the interictal samples. In the first step, in the minimum distance method, at first we calculate the minimum, then we calculate the maximum, then D1 is assigned to the distance between 0 and the minimum, and D1 shows how much the data is similar to interictal. Afterwards, D2 is assigned to distance between 1 and the maximum, and D2 shows that how much the data is similar to the pre-ictal samples. Then we need to compare D1 and D2. If D1 is lower than D2, it shows that the data are most similar to interictal sample. Then we need to assign the minimum to the output. Otherwise, we need to assign the maximum to the output. Here you can see D1 is lower than D2, then out is assigned to minimum value, and then as you can see, because point 13 is lower than the threshold, then it shows that the input is interictal, which is exactly correct. In the training step, to overcome the imbalance data, we use the equal number of samples, and in our work, patient-specific and patient-dependent models are investigated. You can see the number of samples of training and the number of samples for testing. And for patient independent, live-on patient out-cross validation is used. It means that we train the system with the trained samples of 2 patients and test the system with test samples of the another patient. However, for the patient-specific, we train the system with the trained samples of that patient, and then we test the system with the test samples of that patient. In our work, we consider 4 evaluation metrics: area under curve, sensitivity, false positive rate, and accuracy. The last 3 metrics are computed using a threshold of 0.5. Here we can see the performance of the patient-specific model. In this part, we consider 3 different structures: In the first structure, we use Swish as an activation function in both layers without the normalization. In the second structure, we use sigmoid as an activation function in both layers without normalizations. And in the third structure, we consider the Swish as an activation function with normalization in the pre-processing step. In addition, we analyze the performance of the system with three-dimensional post-processing methods, mean, minimum distance, and K of n. As you can see here, for the first structure, the best AUC is obtained when we use minimum distance in the post-processing step, and the AUC is 0.92. In the second structure, the best AUC is obtained when we use mean in the post-processing step. And in the third structure, again, when we use minimum distance in the post-processing, the best AUC is obtained. As we can see here, the comparison results show that the best results are obtained when we use Swish as an activation function without normalization, and when we use minimum distance in the post-processing step. And then the best model here for patient-specific is the first structure. Here you can see the performance of the patient-independent model. We consider two structures, and our goal is to check the performance of applying normalization and without normalization. As you can see here, the first structure, in the first structure, we didn't use normalization. However, in the second structure, we consider the normalization. Again, here we have the three mentioned post-processing methods to evaluate the performance of the system. As you can see here, for the first structure, the best results are obtained when we use the mean in the post-processing step. However, for the second structure, the best results are obtained when we use the minimum distance in the post-processing step. As you can see here, applying normalization improved the result, and this improvement is due to removing the scattering in the data, and in this case we will remove the effects of the minimum and maximum values, which sometimes caused by rank recordings. In addition, we compare the results of our purpose model with recent seizure prediction methods, and it is worth to mention that the mentioned methods are using the same test files to evaluate the performance of their system. For the first one, the first structure is related to the first place in the Kaggle competition, and they use more than 30,000 features in their section. And for the rest, you can see they use different methods in the pre-processing and feature extraction, such as downsampling, continuous Veblen transform, short-term Fourier time Fourier transform, non-negative matrix factorization, and in the classification, some methods such as a multi-scale convolutional neural network, semi-dilated convolutional neural network, convolutional epileptic seizure prediction method, and support vector machine. Comparison results here show that the best model and the best result obtained by our model. And as you can see here, our model has the highest AUC and the lowest false positive rate and lowest trainable parameters. Here we obtain the conclusion. We have proposed an epileptic prediction system based on handcrafted features and a two-layer LSTM with Swish activation function. In our research, we consider both patient-specific and patient-independent models. To best our knowledge, this is the first time that the Swish is used in the epilepsy prediction systems, and simulation results show that applying Swish activation function and applying a novel post-processing method based on the highest similarity improve the results. In addition, simulation results show that applying normalization method in the processing improves the results of the patient-independent model by removing the scattering in the data. To address the problem of the data, handcrafted features are used in this research. And as it can be seen, our model has the best AUC, lowest false positive rate, and lowest trainable parameters compared to the previous work. According to what we discussed, we can see that our proposed model is efficient, suitable, and reliable for resource-constrained applications. Thanks for your attention.